Please don't forget to like, subscribe, and comment. Thank you so much.
Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +2348085095144 to learn more and get started today.
Something that arises because we are not so sure. We can't be perfectly sure about certain measurements. There is no way two people will get a measure a particular quantity and get the same value. It's not possible. That's if the precision of that instrument is so fine. Somebody might get maybe a length of 10.253 centimeter or millimeter. Another person can get 10.252 millimeter. Maybe another can get 10.251 millimeter. For the same length that was measured, different values can be obtained. So we make allowance for all the possible values that can be obtained, when we carry out measurements. So for instance, if you are given 10 plus or minus 0.2, you have a range of plus 0.2 above 10 or minus 0.2 above 10, isn't it?
Yes.
All right. So, for instance, 10 plus or minus 0.2, what are the possible measurements that can be obtained within this range?
10.02,
10.02,
9.98.
So that would be 10 minus 0.2 for the lower bound, then 10 plus 0.2 for the upper bound. So starting from 9.98 to 10.02, isn't it?
Yeah.
9.98 will be the lower bound when you subtract 0.2 from 10. The other one would be the upper bound when you add 0.2 to 10. That's 10.2 actually. Do you mean 9.8 or 9.98?
9.98.
For 10 minus 0.2?
Oh, 0.2, 9.8.
So it should be 9.8 to 10.2. All right. So any measurement, in fact, if this is stated as the uncertainty for that measurement, any measurement from 9.8 to 10.2 will be acceptable. Right? But anything outside of this range obviously falls outside of the acceptable, measurement because it's outside of the uncertainty. Please give me a second. I need to put off this fan. It's making noise.
Okay.
So that's that about that. Uncertainty gives us a range of values that are acceptable or can be accepted in any given measurement. Now, we talk about precision. I've just mentioned precision. Precision is when you get a similar value or values that are close to each other no matter how many times you repeat. I will give you an example. I think I should have space for this. Are you listening?
Yeah.
Let me see if I have enough space for this. I think I should have space. Where is the best place to introduce this? I don't want to use up this space for the work. Okay, let me zoom this out and use this space below. I'm on page, anyway, I'm sharing my screen so you can see on page 10 of 20. I have different measurement. Look at this. Assuming 3 students were asked to take a measurement of maybe a length of a rod, and This way there are different values, 20.2, the other one got 19.8, this one got 20.3, you know, assuming the actual length of the rod is 20.1, you know, but this way the values, all of them got. Then, are you listening?
Yeah.
Okay, whatever unit that could be, centimeter, centimeter, centimeter. Of course, you know when you carry out a measurement, you must indicate the unit. Very important. Okay, now another set of 3 students were required to take the same measurement. And this is what they got. This is what they got. I'm going to write, let me use blue. The first person got 19.5 centimeter. The other one got 19.4 centimeter. And this other one got 19.3 centimeters. Or let's even call this one 19.2. 19.2 centimeter, 19.3, and 19.4 centimeters. Another set of 3 students got this value in blue. These other ones got this one in black. So, which ones have their values close to each other? Close to each other. This is set A. Remember the right measurement, the actual measurement of that rod is the same 20.1 centimeter.
Yeah.
So I'm asking which group of 3 students got their own measurement close to each other or closest?
Each other.
Yeah, is it the group in blue or the group in black?
Blue.
The group in blue, their measurements are close to each other. So precision is usually about how close those measurements are to each other.
Yeah.
It may not be accurate. Something can be precise, but not necessarily accurate. But accuracy is how close the measurements are to the required value or the true value. The true value is 20.1. This one, 20.2, 19.8, 20.3 are, in a sense, more accurate. For instance, if we round all of them to the nearest whole number, what would this be? 20, isn't it?
Yeah, because they are the closest to the true value.
To the true value. So that's about accuracy. Accuracy is closeness to true value. But precision is closeness to each other. You know. Of course, an instrument that is very precise will have measurements to a higher degree of precision. You know, you comparing micrometer screw gauge with vernier caliper or with a meter rule, which one is more precise? Let's say micrometer screw gauge and a meter rule. Which one is more precise?
Micrometer screw
gauge, which can measure up to 0.01 millimeter. In fact, the lowest count, or what we call least count, or smallest division, or precision of a meter rule is 1 millimeter. That's the least value you can measure. You know now?
Yeah.
For a vernier caliper, you can have vernier calipers up to 0.1 millimeter precision. Micrometer screw gauge, 0.01 millimeter, so it's more precise. All right. So when you require measurements that will require a higher precision, you will need those higher precision instruments. So that's about precision, closeness to each other. No matter how many times you repeated the measurement, they are close, similar. But accuracy is when you get values that are close to the required value, but not necessarily close to each other. You know. Now, of course, there are certain errors that can occur in measurement. Systematic error has to do with the equipment. You know, if your equipment is not properly set, assuming there's a 0 error in the equipment, any measurement you take will be wrong or will have an error because there's already a fundamental error. It is not set from 0.
Yeah.
What I mean is you have a ruler that's probably broken and it's not really counting from zero. It doesn't matter how well you try to get a measurement from that ruler, it will not be accurate because the zero error will introduce what we call systematic error. Now, to fix systematic error, of course, you need to recalibrate the equipment and view at eye level to avoid parallax error. Now, systematic error can produce precise measurements which are not necessarily accurate. You know, you may try as much as possible to get all the values close to each other, that's precise or precision. But since there's a fundamental error from the instrument, which is the system itself, it might be precise but not accurate. You get the gist?
Yes.
Now, random error has to do with the error that is due to the person who is carrying out the measurement. You know, so random errors occur when same instruments are taken by different persons or repeated by the same person. Now, to reduce random error, you usually repeat the measurement and then calculate an average. Anytime you talk about repeating a test or a measurement, always include calculate an average.
Like the mean.
The mean, yes, the mean. You need to take, like if you took 3 readings, you need to find the average of the 3. You add all the readings and divide by 3. In fact, when you do that, you also reduce the uncertainty. I will explain to you what I mean by that. Okay, we've talked about smallest division and all that, you know, with the meter rule and what you need to do. Some instruments will set their uncertainty to half of the smallest division. I just need to mention that, particularly if the thing is not given. For instance, for a meter rule, what is the smallest division of a meter rule?
0. No, 1 meter.
1 millimeter. So if the smallest division is 1 millimeter, the uncertainty can be set at plus or minus 1 millimeter.
1 millimeter.
That's plus or minus half of 1 millimeter. It's not a hard and fast rule. Some can set it at plus or minus, usually plus or minus half of the smallest division. Did you get that?
Yeah.
So plus or minus half of 1 millimeter or plus or minus 0.1 centimeter will be its uncertainty. So any measurement you take from that, you need to indicate plus or minus 1 millimeter. Half of, that's 1/2 of 1 millimeter. Okay, all right. I just need to say this and then we move on to something more interesting here. Look at this. I think I need to emphasize this. Sometimes when you carry out a measurement, like you are reading with a meter rule, I think I have to emphasize this. You need to get it right. Look at a measurement you are taking with a meter rule. I am going to draw like this. Calibrated. You see with me?
Yeah.
Calibrated like this. 5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, and so on. Okay, assuming here is 1 centimeter or 10 millimeter, as the case may be, 20 millimeter, or so on. Now, if you have this, you're taking a measurement from here to here. What's the length of these 2 places I marked in blue?
That is 10.2.
Are you sure it's 10.2? Be careful. This is 10. This is 20.
Oh, 10 point.
That's a millimeter. This is 10. This is 20. So is it point?
Okay. 12.
This first
12,
one is 12.
18.
Okay, let me zoom it in very well so that we can see it better. 12 and 18, right?
Yeah.
Let me call here A and call here B. So if I'm taking a measurement from A to B, what you did was value of B minus value of A, isn't it? But you know that when you were trying to read A, you need to recognize the uncertainty in reading A. The uncertainty means someone else could have read something else. And for a meter rule, what's the smallest division?
0,
0.1 centimeter
1,
or 1 millimeter, right? So
yeah,
its uncertainty will be plus or minus half of 1 millimeter, is it not?
yeah.
I told you, or simply 0.5 plus or minus 0.5 millimeter. So in reading A, you need to take into consideration the uncertainty of plus or minus 0.5. In also reading
Mm.
B, you need to take into consideration the uncertainty of plus or minus 0.5, because someone else could have read a different value at A and also at B, even though we are just trying to measure the length A to B. So in reading A to B, what I'm saying is there are two uncertainties you need to consider. The one at A, which is plus or minus 0.5,
So
and
do you now minus the
you add,
uncertainty?
you add the two. You add the two uncertainties. So I said all of this to tell you that a measurement taken with a meter rule read from one position to another position, right? Even though
Yeah.
at any reading, at any point, at any marking, the uncertainty is plus or minus 0.5 millimeters. Also, the other marking, it's also plus or minus 0.5 millimeters. So altogether, the uncertainty will be 0.5 plus 0.5.
Oh, so that'll
Okay.
be 1.
1. So this is the uncertainty in reading A. Also, uncertainty in reading B is also plus or minus 0.5,
Okay.
0.5 millimeter. So when you take a measurement from A to B, the uncertainty will be double of that. So length A to B, we have an uncertainty, whatever the value is, A to B will be plus or minus the sum of uncertainty at A and the uncertainty at B. So altogether 1 millimeter, isn't it?
Yes.
Uncertainty is usually expressed in one significant figure. Take note of this because you're going to see some questions on that. Beautiful. So the true measurement or the real thing we measured is 21 centimeters.
Yeah.
And we recognize an uncertainty of plus or minus 0.3 centimeter.
Yeah.
So what we call absolute, hold on, what we call fractional uncertainty, please. What we call fractional. This 0.3 centimeter is the absolute uncertainty, please.
Yeah.
This 0 plus or minus 0.3 centimeter is the absolute uncertainty, okay?
Yeah.
So what we call fractional uncertainty is that uncertainty over a true value. So 0.3 over 21.
Um,
In other words, fractional uncertainty is equal to uncertainty over true value.
oh, but what's the measured value?
Yeah, it's 21. It's just like somebody measured 21 with a meter rule or any other instrument.
Oh,
And we said,
so
this,
what?
yeah, and then we are saying, this measurement you took, we need to make allowance for certain values that are possible to get with that instrument, plus or minus 0.3 of it, which means someone that got 21.7 centimeter, sorry, 20.7, 21 centimeter plus or minus 0.3, what is the range of values you get, assuming like you are doing lower bound and upper bound?
Um, 21.3.
21.3 is the upper bound. What's the lower bound?
20.7.
Okay, so we are by writing plus or minus 0.3 centimeter, what you are telling whoever is going to use that measurement is anything from 27 centimeter to 21.3 centimeter will be accepted.
Oh, so what's not the point of the fractional uncertainty?
Because we're going to use it for something else. In fact, from fractional uncertainty, we need to know what we call percentage uncertainty. We're going to use it for something else. So just you need to know what that is. By the way, to calculate percentage uncertainty, you just multiply the fractional uncertainty by 100%. What is really important?
Oh,
What is really important is percentage uncertainty. Fractional is just a step to getting percentage uncertainty because we're going to use it for something else. So I will just take you to that.
okay.
Now, just to summarize, if a measurement is given as 21 centimeter plus or minus 0.3 centimeter, this plus or minus 0.3 centimeter is the absolute uncertainty, right?
Yeah.
To get the fractional uncertainty, you use that uncertainty, which is of course is plus or minus 0.3 or simply 0.3, divided by the true value, that's 21. Now, to get the percentage uncertainty, just express it as a percentage by multiplying by 100. Yeah. Now, the reason for all of this is when certain measurements have some composite functions. What I mean is, like something reciprocal, something you need to do something. Okay, I think always the test of the pudding is in the eating. Let's just go straight to a question. Let's just go straight to a question.
Okay.
Before I submit, pardon?
Oh, I thought that was a question.
Oh, that's a question. Let me just say something.
Okay.
When you have, for instance, if a is equal to x squared y over z, and x and y have their uncertainties. The uncertainty in A, I hope I'm not jumping the gun. Okay, I think I need to give values, but this equation would have just given it very well. Okay, let me give values, it will help you to understand it. Look, assuming y is measured at 1.5 plus or minus, no, that's too small. Let me say 15.
Hey, what are we doing?
Pardon?
Why am I saying X, Y, and Z?
I'm giving you an illustration before I answer the question. I need to establish some points first. Are you listening?
Yes.
15.0 plus or minus 0.2, and this one is 18 plus or minus 0.1, and this one is maybe 750 plus or minus that will be 2. Okay, let me say plus or minus 2 or 1,750. Let me put it like that, plus or minus 2. What's the value of A, by the way? A itself, just calculate A. Do you have your calculator? X squared, which is 1,750 squared times Y. What is Y? 15 divided by Z, 18. Do you have your calculator there?
No, but I can use the one on my iPad.
Okay, please, can you do that very quickly? Because I want to explain something to you.
Okay. 18 divided by what?
You are supposed to solve this. You can see their values. Only the values, the true values you're going to use.
Oh. Okay. So that's 100 and is that 1,000?
Okay. Or can I just call it 750? 750 plus or minus 2, whatever the unit is.
750. Should I actually put plus or minus 2?
No, you're not adding plus or minus 2 in finding the value of A. This is just to give whoever is using the measurement the range of accepted value. Uncertainty is just to show the person, like you're using a product. Oh, this is the accepted region. If this thing is outside of this region, it is a defect. Don't use it. But if it is within this region, it's still acceptable. So the main thing is the true readings.
Plus 15.
That's times
X. Oh, sorry, times 15.
X squared times 15.
Divided by 18.
Yeah.
And that is...
So 750 squared times 15 divided by 18.
468,000.
468,750. 468,750, right? Okay.
So did you hear me?
Yeah, I heard you. 468,750, you said?
Yeah.
All right, that's A. Now, in expressing A, because A is composed of all these other values, in expressing A, we need to also write it in with its uncertainty. So what is the uncertainty of A? Are you listening to me?
The uncertainty of
We can't use zero
yeah.
point 0.2 only. We can't use 0.1 only. We can't use 2 only. We have to consider an appropriate uncertainty that captures all of them. Did you hear me?
Oh, how do you do that?
Beautiful.
Yeah.
That's a good question. This is the way we do it. Interesting stuff. This is the way we do it. When you are multiplying or dividing, just add the percentage uncertainties. That's the reason for that percentage uncertainty I was telling you about.
So when I'm multiplying, I should just add.
The percentage uncertainties.
So so if I'm dividing, I should not.
Whether multiplication or division, add the percentage uncertainties. Did you get that? Can I say that again?
Yeah, they hear.
Let me say it again. First of all, addition and subtraction. Simply add the absolute uncertainties. Add
Okay.
absolute uncertainties. This is now the beauty of where the thing comes into play. Now, multiplication division or par, simply add percentage uncertainties.
So you're always just adding.
What, can I hear you better?
You're always just adding.
Yes, but then, exactly. But there are different things we add. When it is an addition or subtraction, you just add the percentage on the absolute uncertainties. What I mean by that is, look at a situation like this. If I had a letter C, which is x squared, or let's say y minus x, y minus x. Give me the value of y minus x from the values we have. There's no x. Z minus x, z minus y. Z, if c is equal to z minus y, what's the value of c from the values we were given? I use your calculator. Okay.
Z minus y. Z is
18 minus
18 minus
15. That gives us what? 33, I guess, 33 units, isn't it?
Not just 3.
33 now. I said 8. Oh, minus. Sorry, don't mind me. I was adding in my head. 3. Okay? You're right.
Yeah.
3 units. Now, what is Z plus, let me call it another letter, let me call it B. If B is equal to Z plus Y, what is B?
P equals Z plus Y. P is
The same Z, 18, Y, 15.
Oh, 18 plus Y. Isn't that 33?
33. Okay, now, these are the true values of B, C, and A. But they must also have their own uncertainty because the values we use for their calculation had uncertainties. So what uncertainty are we going to add to C? What's the rule for simple addition and subtraction?
Just add the uncertainties.
Add
The
the absolute
absolute
uncertainty.
uncertainty.
And all these things written here are the absolute uncertainties. So
So you don't have to divide it by anything.
you just add the absolute uncertainty. So C will be equal to what? 3 plus or minus what?
3 plus or minus.
Just add the absolute uncertainties.
Oh, 0.2 plus 0.1.
0.2
That's
plus
0.1.
0.1. That gives us 0.3. So the value of C is actually 3 plus or minus
Plus
0,
or minus
0.3.
0.3.
What about B? 33 plus or minus
Same.
what? 0.3. So whether it is, you see, you're cool, you're good. I knew that. Whether you are adding or subtracting, just add the absolute uncertainties. But when you are multiplying or dividing or raising something to power, add the percentage uncertainties. Right?
Okay.
So in
The percentage.
yes, the percentage uncertainties.
Then how do you find the actual uncertainty?
So let's go. Let's find the percent, but you will still have to convert back to absolute uncertainty later. Oh my goodness. All right, let's find the percentage uncertainty of each of them. For y, it is 15 plus or minus 0.2. So what is its percentage uncertainty? Remember, it is
0.2 over 15
50
times
times
100.
100. Beautiful. The one for z will be
And 0.1 over 18 times 100. Should I calculate
please
it?
calculate it. Let me just write the percentage.
Okay.
Percentage is 0.2 over 15 times 100.
0.2 0.2 over 15 times 100 is 1.3333. So 1.33%.
Okay, let me call it 1.33%. We won't even use all of this. Okay, what about the one for 18? That's 0.1 over 18
divided by 18 times 100. That's equals to 0.55%.
0.55%.
So 0.56% actually.
Very small. Yeah, I forgot to tell you something, but I have mentioned that to you before. Now you will need to be using this. In writing the value of A, right, it should be expressed to the number of significant figures relevant to the smallest significant figure we use in the calculation.
The smallest?
Yes, the smallest. Whenever you are multiplying or dividing or raising to power, the answer should have a number of significant figures equal to the smallest value of significant figure we use in the calculation. Like y is 15.0. How many significant figures?
15.0. That's 3.
3. Z is 18. How many significant figures?
3.
18 is 3 now. It's 2.
Oh, sorry, 2.
And x is 750. How many significant figures?
3.
Hello? In some
750.
Yeah, only 2 significant figures now. The 0 is not significant.
Oh, yeah.
So what's the smallest significant figure?
Oh, you have the 0 no significance.
Just like if it was 75326 and you were asked to round 753 and you were asked to round it to 2 significant figures, what will you write? Is it not 75? Since this is not up to 5, you call it 750.
Oh, okay.
Because if it was 753 and then you're asked to round it to 2 significant figures, you write 75, the 3 is not up to 5, so it will be changed to 0. So this is actually 2 significant figures, okay?
Okay.
All right, don't worry, we soon round off and then we'll continue later. By the way, 468750, what is the appropriate number of significant figures I should round it to?
2.
2, so this thing should actually be
47,000.
470,000
units.
Okay, so we need to also get its absolute uncertainty. I is percentage uncertainty. That's percentage for this one is, we got it as 0.56%. Percentage for this one, we got this 1.33%. Let's get the percentage for this other one so that we can make sense of this. Percentage of this one is absolute over true value, isn't it?
Yeah.
What's the absolute?
Absolute is 2.
2 over 750. All these things are too small. They are really very precise. Times 100. So what does that give us?
Times 100. That's equals to 0.267.
0.267, so 0.27%. Okay, finally, we have gotten all their percentage uncertainties. And it says we should add, for multiplication, division, and power, add percentage uncertainties, isn't it?
Yeah.
I hope you know that x squared simply means x times x.
X times x. Yeah.
So it's just like saying the first for the first x, the second for the second x, the one for y, and z, or simply multiply the one for x by 2. Because it's saying x, y over z. So so let's just add the percentage uncertainties. For x, what are we going to have?
X was
1.33 still here.
1.33.
So we have.
So that's 1.33 times 2.
Beautiful. So
That's
you just multiply
2.66
plus
0.6.
56 plus 0.56. Please be typing it out.
Yeah. So that's 3.22.
Plus.
Then plus what again?
0.27.
Plus 0.27.
Okay. So that means the real value of A is actually what?
3.49.
3.49%, right? So the real value of A will be 470,000 plus or minus. Are you getting that?
Yeah.
Plus or minus 3.49%, you said, right?
Yeah.
Now you still need to change it to absolute. It's usually awkward to write uncertainty in percentage. So what you need to find, what is 3.49 of 470,000 to change it to absolute percentage?
3.49 divided by 100 times 470,000.
Yeah.
That's 16,403.
Ah, that's a lot too. 16,403, right? 403. Okay, so 16,403 is the absolute uncertainty. So in writing the value of A, what should we actually write? All in proper uncertainty. What did we even get for the value of A? 470,000, isn't it?
Yeah.
470,000. So it will now become, the real value of A is now 470,000, right?
Yeah.
Plus or minus?
Plus or minus 16,403.
And I told you uncertainty is usually expressed in one significant figures. So you can.
Oh, so that's just 16,000.
One significant figures.
No, 20,000.
20,000. So anything from 470,000 plus 20,000 or less will be an accepted region. Okay, we continue with more examples in our subsequent discussion. So I just want you to practice this. Let's just go through the question, we'll walk through it. First of all, it says, make estimates of the mass in kilogram of a wooden rule. Just estimate the mass. the volume in centimeter
I
cube.
should just estimate, like I should guess.
Yes.
Because I also don't understand estimation. So I might just put in any number I want.
And if you like, put 50 tons. If a meter roll is 50 tons, okay, so you can put any number you like. It has to be a reasonable estimate. Can I give you a way to go about this? A meter rule is a wooden meter rule will weigh about the size of an apple, the mass of an apple. The mass.
How am I meant to know the mass of an apple?
You should know. You have an idea of the mass of an apple. What's your own mass?
I don't know.
Well, you should be about 60 to 70 kg. Now, an apple should be about 100 grams, which is 1 Newton. Right? An apple is about 100 grams.
Yeah.
You know, it's a reasonable apple. It's from 50 to 120 or 100 grams, which of course the weight will be 1 Newton. So if you state any value in this region up from maybe 50 to 200 grams, or the right unit in kilogram, it will be marked for you. It's just an estimate. But it has to be a reasonable estimate. Then it also says in volume something of a cricket ball or tennis ball. You know how a tennis ball, the size?
Yeah.
Volume of a sphere is, I think, 4 pi r cube over 3, isn't it?
Yeah.
It's a slight correction. I noticed a small error in calculating the total percentage uncertainty for A. So instead of using the proper uncertainty of x squared, which is actually 2 squared, I think we used the one for y. We squared the one for y instead. It should have actually been the percentage of uncertainty of x, which is this, times 2, as this plus this. I think this is the percentage of uncertainty of x, yes, because x is 750 plus or minus 2. So it should actually be 0.27 plus 0.27, or 0.27 times 2, because of the x squared, before we add the y, which is 1.33. And we can then add that of z, which is 0.056. I think that's going to change the value we got here. This 3.49 will be different. It will definitely be different. I think the correct answer should have been, let me quickly change that so that we can take note of that. It should actually have been 0.27 plus 0.27, that's the percentage uncertainty in x, which is 0.27 times plus 0.27, or 0.27 times 2, then plus again 1.33, and then that is for z. For y is 1.33, the percentage uncertainty for y, then plus again 0.56, that's the one for z, which is 0.56. I think the real thing should have been 2.43. So what we have here should actually be 2.43. This should be 2.43. So that needs to be corrected. 2.43. 2.43. I observed that when I was going through this. 2.43. So what we should have done is that 2.43, we find the absolute uncertainty times 470,000, 1, 2, 3. So that should actually be 11. So this should be corrected to be 2.43 instead. 2.43. That's 2.43, the corrected value, times that, 2.43 times that, I think that should actually give 11,000 something something something, but we round it to one significant figure. That should be 11,421, 421, and then we will round it to one significant figure. That should be 10,000. That should actually be 10,000 to one significant figure. So what we should actually use is 470 plus or minus 10,000 as the absolute uncertainty for A, you know. So just that correction we need to take note of. Okay. Now we need to understand that there are certain rules we adopt in expressing the number of significant figures of absolute uncertainty. So how many significant figures should one give in stating experimental uncertainty? There are 3 rules. We usually, like I said earlier, we usually express uncertainties to one significant figure. For example, if we have 3.45 plus or minus 0.015, to one significant figure, it should be that the uncertainty, absolute uncertainty to one significant figure should be 0.02. So that is, this 0.015 should be expressed to one significant figure, which is 0.02, stopping at where we have figure 1. So the final answer will now be 3.45 plus or minus 0.02. That's one rule. This is one of the rules. The second rule is now if we have, for instance, the significant figure of the first significant figure of the uncertainty as 1, like this 1.5, we can express it to 2 significant figures. As if the uncertainty starts with 1, if the uncertainty, absolute uncertainty, starts with 1, like 0.15 or even 0.015, because the uncertainty starts with 1. In that case, we might decide to express it to 2 significant figures. That happens when the uncertainty, absolute uncertainty, starts with 1. Like in this case, 3.45 plus or minus 0.015. The absolute uncertainty starts with 1. So whenever an absolute uncertainty starts with 1, you are at liberty to express it to 2 significant figures. And so we can leave it as 2 significant figures, which will now be 0.015 plus or minus 0.015. So if you use this, it will be marked. If you use this, it will also be marked for an experimental uncertainty. Now the next rule, that's the second rule I've talked about. I said the first rule is the general rule of thumb: express uncertainty to one significant figure. For instance, the 3.45 plus or minus 0.015, the absolute uncertainty should be expressed to one significant figure, which will now be 3.45 plus or minus 0.02, which is one significant figure. The other rule is, if the absolute uncertainty starts with 1, you can express the uncertainty to 2 significant figures, like 3.45 plus or minus 0.015, it starts with 1, so we can express it to 2 significant figures. Now the third rule is, if the absolute uncertainty has 5 after the first digit, That's if the second significant figure is a 5. If the second figure, not the second significant figure, if the second figure is a 5. For instance, 3.45 plus or minus 0.035, the second figure is a 5. The second figure is a 5. The second figure is a 5. After 3, the first figure, the second figure is a 5. So we can express it to two singular figures. So mostly it is 1 and sometimes 2 significant figures. Usually it is 1 significant figure and sometimes 2 significant figures. You can use 2 significant figures if the first digit is 1. If the first digit of the absolute uncertainty is 1, you can use 2 significant figures. Or if the second significant digit, or if the second figure in the absolute uncertainty is 5, you can use 2 significant figures. So for instance, this question we got here, we actually had 470,001 plus or minus. Let me write it the way it was initially. We wrote it as 10,000 because we express it to one. This is the absolute uncertainty, 11,421. So we express it to one significant figure, which is 10,000. But if you notice, the first figure is 1. The first figure is 1. So we can express it to 2 significant figures. In that case, it can be 11,000. Because the first figure is 1, so we can express it to 2 significant figures, which is 11,000. So the answer becomes, the value for A is now 470,000 plus or minus 11,000. Don't forget the rules. 3 rules. The general rule, which is usually 1 significant figure. The second rule, which you can express to 2 significant figures if the first digit is 1. And the third rule, which you can express to 2 significant figures if the next second digit is a 5. If the second digit is a 5. That's that. On uncertainty and measurement techniques. Like this says, a unit may be stated in a prefix that represents a power of 10 multiple or submultiple. And all this, as you can see here, and then it's asking in the following list, underline all the units that are SI base units for ampere, coulomb, meter, Newton. And then we have this, the potential difference V between 2 ends of a uniform metal wire is given by this. Where D is the diameter, L is the length of the wire, I is the current, rho is the resistivity. Now, some information we have concerning those item quantities is provided here. Remember, V is 4 rho Li over pi d squared. And then the question says the quantities listed in the table have values that are used to calculate rho as 4.1 times 10 raised to the power minus 7 ohm meter. Now for this value of rho, that's the resistivity, calculate the percentage uncertainty. Just a little hint. In doing this, of course, you need to make the resistivity the subject of formula. Before we can do all that. And we use these values and their the percentage uncertainties to be able to calculate what is required. First of all, the percentage uncertainty and the absolute uncertainty. of the resistivity. That's a formula that we need to make rho subject of formula. And here we have another question. Measurements are made from a sample of metal wire. It's similar to the one we did. The length, the diameter, the resistance, all given their values and their uncertainty, the absolute uncertainty this time around. And we say state the appropriate instrument used to measure length, diameter, resistance. From there, it says we should show that the resistivity of the metal is calculated to be 4.86 times 10 to the power minus 7 ohm meter. Normal formula for calculating resistivity. Resistivity is resistance times length over cross-sectional area. Or yes, resistance times length over cross-sectional area will give us resistivity. Now it says show that the resistivity is this. That's all we're going to do to get that, and then calculate the uncertainty in the resistivity, which of course should be expressed in absolute uncertainty. You know, we still have to get the formula for resistivity. Using these values, we'll now be able to the values and the absolute uncertainties. We get their percentage uncertainties, and then we're able to get, first of all, the percentage uncertainty, and then the absolute uncertainty. Then it says use the answer in B to express the resistivity with its uncertainty to the appropriate number of significant figures. Like we explained earlier, the 3 rules for expressing uncertainty that will be applied here to the appropriate number of significant figures. Any of those rules will be appropriate here. So these are some practice questions. Let me zoom out to see if we can see the questions better. The first question and the second question, they are all related. And they are basically about resistivity. Applying the principles we have discussed, this should be a very easy question. Okay.
Please don't forget to like, subscribe, and comment. Thank you so much.
Welcome to Like Learning School, your premier online education platform. At Like Learning School, we are dedicated to helping students and learners unlock their full potential, providing them with the foundation, support, and guidance they need for academic excellence. Our platform caters to 2 main target audiences. Firstly, we work with school children of all ages, offering academic follow-up and accountability partnerships. Our seasoned tutors provide personalized attention to ensure students stay on track and reach their goals. Secondly, we support students and learners who are preparing for internal, external, entrance, or professional examinations. We offer comprehensive and well-structured support to help them achieve outstanding performance in their exams. Our robust virtual courses are designed to keep students engaged and motivated. With interactive videos showcasing our teaching sessions, students actively participate in the learning process, making education enjoyable and effective. But that's not all. We believe in personalized education. Our students have access to personalized tutorial sessions, whether online, physical, or hybrid, tailored to their unique learning needs. Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +234 808 509 5144 to learn more and get started today.